It was a missing table, or it was a.
You could solve it with the table that he gave us, but I personally did it with a different table. Yeah, that table wasn't on there. Exactly. Shaking my fist there. I'm upset. Yeah, some of it. Yeah, I think I got it. I mean, it's fair there. I think it's fair again under like one person gets a business. You know what I mean? Yeah. Before it ever like take place.
Okay. Ready? Dynamics. Are we ready? Not ready? I saw some head nose. No, not ready. Ready. I know it sounds like midterms are ramping up, like first round of stuff coming through. No exams, at least in this class, so we have like a little bit of something. We can just come in, try to learn something. Imagine that. Go to class and try to learn. Crazy. But what do we have so far? Mostly, I mean, right now, main thing is we're just working through, so just starting off with like logistics, working through homework 2. We looked at torque and like motion, rotating motion last time, and then started to look at like what happens with mechanical advantage with this like 3-bar system for today, for Monday. But I wanted to check in and see, like, did you figure out what the moments are equal to for this total diagram? Like, what is the sum of the moments there? I'll scroll up a little bit so we can kind of see it. Figure out what is that moment? Like, what's the total moment? And here, like, the fancy way of like having a moving thing, but you set all the MA terms equal to 0, is you say it's quasi-static. So either the bars are massless, like they have no momentum, or they're just moving slow enough that it's not a dominating effect. And this comes up a lot in all sorts of engineering analyses. But this was the next step. What is that sum of the moments? What are the forces? What moments are acting on it? Break it up. What do you mean?
Like split it up.
Oh, you want to split it? Yeah. You can do that.
Because I need to do about 1 point, right? Yeah. So I think we're not.
You could split them as 2. Yeah. No matter what, split them or put them together.
was looking through the text message. There was one so you know what it's interesting that works yes, you know, like that's what means for long too. Yeah, I don't need this table. I'm not trying to Are you doing like as a picture or maybe like we're changing it like that? Oh, you know, we can find you. Yeah, we can find you. So then once you do that, yeah, no, sure. Because then, yeah. Not the table. I had like it's kind of like a triangle, and then a piece of that. It's like down, it's just like triangle. Well, you kind of have to. I had it in my notes because we went over it in class. Your shoes, It's like this, yeah. It's like a weird triangle. I don't know, that was a shock. It was not like a practice. It was always like the one from last time. It was so easy. I was like, oh, this yeah. Yeah. I thought it was going to be See, that's like, yeah, that's like a dice idea. Also, like, you know, like, so like, I know it's How bad is it? Oh, you think this is like. Yeah, type in your Excel. You might be able to get a wave. Shoot. Well, I mean, if you take some of one, but they didn't do the third. Yeah, so they're gonna check it. Like, I wouldn't take that risk. I would just go. Because if you're gonna take it, especially if you're gonna take the external question. Oh, that's a good question. It's gotta be good, yeah. Totally gotta be.
All right, so first question is, when you're taking moment, what is the, like a moment is a force times a distance, right? So what distance are we dealing with? Am I echoing again? So what distance do I want to use? Yeah.
A distance that's perpendicular from the force.
Okay, perpendicular force to what point?
Depends what point you choose.
Okay.
So if you choose to calculate moment from, I guess that's a 0 or O.
Yeah.
Then you would use the perpendicular, like for force A, or force F at A, you need the perpendicular distance from it.
Okay, something like this, right? I could say these are my moment arms, like RA and RB, and that's for a given 100 Newton force, it's RA times 100, something like that. So we could say the moment around O is RA times F, positive or negative?
I got negative.
Negative, yeah. Looking at into the page. And then N, positive or negative, RBN. Positive, yeah. So like twisting kind of that way. Cool. What about those? What about reaction Y? Oh, wait, let me get myself off the screen. There we go. What about reaction Y and N? Are they, or sorry, not reaction Y. RX and R. How much torque are they creating? 0? Because they're like, their moment arm is 0. Their force is not 0, but the distance from our chosen point O is 0. All right, cool. So this is good. So now I know that F equals negative RB over RA times N. Or vice versa. I guess I would want the opposite, right? Because I know what F is, I can solve for N. So that normal force is now going to be, what are these distances? 40 and 70. 100 Newton, not 100 N's. what about that reaction? All we wanted was R, and we're solving for all this other stuff. What's missing now? How do we get to like R? Yeah.
R would equal Rx.
Yep.
So
R is Rx. That's true.
if you find Rx, you can find R.
Cool.
But I'm not 100% sure about that.
Okay. Yeah, yeah. Yep.
Could you just find the moment at A?
Switch it up.
Yeah, which was AX or Rx and R. I don't think it's really good.
Okay. Yeah, yeah. All right. So maybe we chose the wrong point. Maybe O was, oh no, something. Now we want to do some of the moments about A. What does that look like? We still, so now I gotta, so positive, or F has no effect because 0 moment arm. And now RY is, let me get these distances. So this is 40, 30, and then 30. All right, so now I've got sum of the moments around, got a negative 40 times RY, and then a positive 30 times Rx, a negative 30 times R, and then a positive 30 times N. So I know Rx and R are equal. So I could say that this is 30R minus 30R. Or I could just get rid of the whole thing. And I still end up with an equation of that N is 4/7 of F. Once I solve for the fact that N and F have to add up to F, the N plus RY have to add up to F, and then 3/4 plus 4. Oh my god, 3/7 plus 4/7 has to be 1/7. But anyway, so I still end up with the same, basically the same equation. And that was a great exercise of like, it doesn't really matter where you take some of the moments. If stuff is moving and you have like some of the moments equals a change in angular momentum, then it matters a little bit, but not really. You can force your way through it. There's easy spots and then there's hard spots. So the easy spots are whatever point is not moving or the center of mass. Then the hard spot is like it's moving plus rotating. Then you have to factor in lots of other stuff. All right, so we're still a little stuck because all we know, now we know N, and we can solve for RY. So we have RY, we have N, like we can solve for all this stuff, but still not R, that main like R value. Yeah.
Well, if you know RY, then you can find Rx using trig. And then once you know Rx, you can find R.
Okay. How do we use trig for Rx and RY?
You know the dimension at that time, which is like 40 by 30 or 30.
Yeah, it's like a 3, 4, 5 triangle. So we have like
Get,
length 5.
Angle, but I think it's like tan theta equals to RY.
tan theta is Ry over Rx? Why is that? Opposite adjacent. But is there like a fundamental why would the Rx Ry, why would they have to be tan theta? Because it works sometimes and then other times it doesn't. In this case, it does, but why? Why does it work for us? Yeah. So in this case, like the linkage is carrying the load through the bar itself, right? Like all the entire force vector has to go through that bar. So we could use that information and say, like, here, I'm gonna say this. Call it like an R1 for like link 1. So that the total like vector of support, like how much load that bar can hold, has to be in the same direction as the bar itself. I think that was like roughly that tan theta argument, is that because the vector is pointed along the bar, the only way for that to happen is that Rx plus Ry, when you add them up, they point in the same direction. We could do that. Bless it. Equals opposite over adjacent, like that. Do you know the quick way to find like sine, theta, cosine with all these? Since we know that it's a 3, 4, 5 triangle, we don't have to find the angle, then we can calculate all that, right? Equals opposite 3 over 4. Because if we find angle 1 and take the tan theta of it, we're going to just get a rounded off version of the ratio of the lengths. Same with like and you can do it for any XYZ, like if you know, or ABC. If you know the lengths, you don't have to find the angle. You can just get the sines and cosines with the actual lengths. So that would work. So then what's RF? Do we know now? Is it done? Did we solve the problem? What's our Rx then? What do we get? I think that was the goal. Like find Rx. Save the princess. I think this one was this wasn't the sign for everything to do, but it'll work.
Velocity field.
Well, because we know N didn't know. We didn't what R1
They kind of go to the gym after class. Yeah, and then I'll be locked in. I'll be ready to feel completely free. Then I go to my range, then
I guess one thing that we were kind of looking at before is that we found this capital N, but in this case we're using RY. Overall, they have to add up to 100, so if one of them is 4/7, the other one's got to be 3/7. In case you're like, what the heck? He said he wouldn't give me steam tables here. Too soon.
couple hours.
Okay.
So getting invited to
Okay, and then just go back to yeah. Something like 57 newtons, something like that. 4/7 ends up being 4/7 times 100, which means that R is 57, N is 57. Because that's 57 is 4/7 time, or 0.47 is 4/7. It's 45 degrees, right? And we just went through that, like it can only carry a load along that member. So we did all this extra math when we could have looked at it from the other side and said, if it has to carry a load along a 45-degree angle, this load is that load. Like it's got to be equal to each other. That's all right. We learned the process. Learning is a process, right? And now next time you see a 45-degree angle, you're like, this is gonna be easy. Everything, it's all coming together. But yeah, we got there. So that's a nice way, like thinking about where the vector is pointing. That's a good way where it gives you a little bit more information, like geometric information. Another thing that you can do, and we don't have to go through it, but we can take, so we had N like this, R like that, F. Because I saw some people start to do this. And then RX. You can take these this free body diagram and split it into two and look at like what are the internal forces acting, like how is this system connected to each other? Sometimes that's really helpful information. Like if you want to know how much stress a joint has on it, then you need the internal forces. And you can't get internal stuff from big free body diagrams of the whole system. So I could take these two parts and say there's an F here, some kind of like AY and an AX. I still have RY and RX. Then I add another one, still have N, and I still have R. This AX was pointing left, now it's pointing right. It's pointing down, now it's pointing up for AY. And then F, you just choose one, because if you add them back together, all the internal forces should add up to 0, and the total F should just have 1F, not 2F when you add it back together. But if you do it, if you split it up this way, then you don't go through any of that like trig work. You're just plugging and chugging into more F equals 0, sum of the forces equals 0 equations. So if you like just increasing the number of unknowns and just solving for one unknown at a time, this is the way to go. If you're more of like let me see the triangles, get them all connected, then that's the way.
So in this method, it's just like you solve like maybe like just choose the right side, and those values can be plugged in on the left side.
Yeah. So then we have a new equation, like sum of the forces of X is AX minus R. Sum of the forces Y is AY plus N. And then sum of the moments about, here I'll use like point B, like over here. It's going to be negative 30 AY and positive 30 AX. But I end up with new equations, 2 extra unknowns, but I end up with 3 new equations, and I have enough equations to solve for all of my unknowns. Sorry, I keep cutting it off with my chatbot. Yeah. And then I could add up the left side as well and get 3 equations there, solve for A, figure out how AX and N, or AX and RX are related and all that. We got some time. Alright, so we got some cool. I don't think there's never like an auto replay. We're going to start, now we're looking at like moving systems, and we don't really care about the forces involved. We just want to figure out how is motion constrained within these. Like when we have these pins that are forcing these things to connect to each other and it's moving, how does one motion affect another motion? So before we start jumping into like the numbers of like plugging in equations, we want to do something first. This has like a lot of moving parts. So if you want to jump right into this, we can, but usually it's a little hard. Sometimes it's easier to go back to the first thing that we were dealing with. Of like, let's say we have just 2 moving parts. So I only have like 2 angles that I need to deal with. And then 3 like positions that are kind of moving in this part. Or I could call it like the origin O, A, and then B. So when I think about like the vector of the origin, what is that thing doing? Is it moving anywhere? It's like pin, I guess I don't have a specific pin to the ground, but it is pinned right to the ground. So what's happening to the origin, to O? Like as far as its motion, does it have a velocity? No. Okay, good. No velocity. I agree. Yeah, it's not moving anywhere. So position, I can say like position O, velocity O, acceleration O, it's all 0. Everything about O is 0. What about A? What is point A doing as theta is increasing? Let's say it's just every second it has another 10 degrees, like 10 degrees per second, just keeps going and going, rotates around in a circle. What is A doing? Yeah.
Which part of the system is moving? Because you said that O is at the point, so what part is moving?
In this one, O can't move, but A moves up and around, and then B can slide left and right. Yeah. Yeah. Sometimes, yeah, it's hard to draw like motion in just 2 dimensions. Do we have? Go right into the graduate course, right? What am I looking for? I thought I had a nice like. I thought I had an animation of it, but I can't find one. It's not there. All right, sorry. I thought I had like an animation here of a slider crank. I didn't mean to scare you with like graduate. But anyway, yeah, this thing rotates, and then this thing follows it. So like slide over. Yeah. So when we think about like what I'm asking, like what is the motion, like what are things doing, really we're talking about like vectors of what is its position and how do those vectors relate to each other. So one thing that we can do is start drawing like, all right, from O to A is a vector. From A to B is another vector. And then point B, if I just describe like where that slider is, that's another vector. And they're all connected in like a loop like this, right? So based on the vectors that I just drew, what is And here, let me draw. This is RA, and this is RB with respect to A. What is RB? How do I get to B if I want to describe it with RA and RBA? How do I put those vectors to get together? You subtract them, add one, subtract another. You get from A to B by going up to A first.
Did you add RA and RB?
Yeah. And really we're kind of like rederiving relative motion kind of equations, but I can say that this is RB slash A plus RA. If that's position, what's the velocity? Do I need new vectors defined? Thinking or hoping that someone takes the lead. No idea. Yeah. Possible in that 0.01. No, it depends. That's always a problem. So if the vector B can be described as like vector VA plus vector A, what is velocity of B? Yeah. Do you know? Yeah. Yeah, it should be similar, right? All right, that's okay. It's not like I'm expecting you to come here and be an expert in this field. Yeah.
Would it also be like the velocity of the x of with respect to VA?
Just the x component?
Yeah. Because it looks like it's just going to move in the x direction.
Oh, that it's going to move left and right? Oh, I see. So we could say that there's a constraint on it. VB like in the I direction, something like that. To say that it always has to move left and right. It could be any number, but it has to be left-right number. Yep. Yeah, we can say that. That's a nice like geometric constraint on its motion. But even if we didn't have that constraint, the fact that we have those two links together, VB, well, I'm going to delete this for a second. VB is the change in RB. So like going back to, because we don't have to do like any real math. We have to do a little, like we do have to use some calculus, but not like sines and cosines or anything like that. We're just trying to figure out like how our velocities constrain together, which is d of r b slash a dt plus d of r a dt, or VB is velocity BA plus velocity A. So if I have any combination of those velocities, I can solve for. Or if I know VB, like if I know that B is moving to the left at 10 meters per second, I can say how fast is A rotating, like how fast is that moving, something like that. So yeah, I mean, it's not no math because we do need to take a derivative, but it's not like really difficult derivative. It's just saying that position and velocity are one derivative away from each other. And the reason that's helpful is like, what do I want to do? Let's take all this. Like I can write the position of RA in terms of that angle. Like if the angle is the only thing that I'm measuring, I can say the length times cosine is its x position, length times sine is its y position, and as that angle keeps increasing, it's going to move around in a circle. Sine and cosine just describes a circle like that. And velocity of A is derivative there. Oh, if I could do derivatives, but I can't, a negative. So now I have a description of both where it is and where it's moving for that, like point A. And I can do the same thing for BA and the other terms. And now we're getting into like the more do some math, get into the numbers. This one looks like I burned a few fuses along the way though. But the starting point, at least for these kind of moving systems, this is a great way to start, is like what are the points that are moving and how are they connected? And once you create like some kind of vector loop like that, now you can start looking at like the math behind it, like the sines and cosines and lengths and all that. So we'll do the same thing here where we start looking at these different vectors. And as long as we're like creating a loop, we can add them up or subtract them, however we want to do it, and come up with a description of these are the constraints on motion for like a vector analysis. So that's our next step. That's for future class, not for now class.
Thanks a lot.